All right. Hi, I'm Ellen, a grad student here in UT Austin. So in this study, we're trying to use Herschel Spire to survey 27 embedded protostars and trying to characterize their CO emission all the way from J equals to 4 to 3 to J equals to 13 to 12. And we try to learn or find any underlying physical processes that actually contribute to those CO emissions from the study. And there are a few things we have learned from this study. One thing is when we did a rotational diagram analysis and just collect all of the rotational temperature components we found, and we put in the distribution, we actually found there's a two distribution of the rotational temperatures in the 27 protostar we surveyed. And there's a primary population at 100 Kelvin, and there's a secondary warmer population at about 400 Kelvins, while the 100 Kelvin components is mostly correlated with the existence of the envelope, while the 400 components is more due to the cavity shocks. And I'll jump to the last one, which will be on my poster.
I'm an undergraduate here at UT. My advisor is Dr. Kristen McQuinn, and I'm looking at the frequency of starbursting dwarf galaxies. So to that end, we want to understand whether or not starbursting dwarf galaxies are internally driven or externally driven with something like a galaxy merger. And we want to use the duration, we want to use the statistics we get building a sample to figure out the duration and intensity of the bursts to help constrain current galaxy evolution models. To do all of that, I look at resolved stellar populations from the Hubble Space Telescope of dwarf galaxies and put them through a CMD fitting technique, which gives me star formation histories, which I can use to identify the starbursting periods. If you want to hear more about that, come talk to me.
Hi, my name is Jonathan Cohn. I'm a second-year grad student at Texas A&M University. And so I'm working on star formation histories of extreme emission line galaxies. We get our data from the Z-Forge survey, which is just a deep near-infrared medium band survey with photometric redshifts that are accurate to about 1 or 2%. We've identified a population of extreme emission line galaxies. I've got an SED of one of those over here on the left. These are just galaxies with very strong O3 and H beta emission lines. And then we're using the Prospector Alpha model to get a bunch of properties from these galaxies. I'm focusing on the star formation rates, and specifically the star formation histories. So we're stacking the star formation histories for extreme emission line galaxies, comparing those to Lyman-Bright galaxies. And if you want to hear more about that, come see my poster.
Hey everyone, my name is Alex Riley, and I am also a grad student in Texas A&M. I'm a second year and I'm working with Luis Jagari. And I'm specifically looking at debris disks of nearby stars in the gamma ray emission. So normally you think about large bodies grinding up against each other in these debris disks. They make dust. That dust re-emits light from host star in the infrared, and we observe them in infrared. We extrapolate back up to the larger bodies. However, Fermi has actually observed the moon in gamma rays. And so they looked at different particle reactions that could cause this. There's one in particular that requires cosmic rays to burrow through at least 1 meter of rock. So the concept is if we can look at these gamma rays and see gamma ray emission coming off of debris disks, that's a direct probe of 1 meter and larger up bodies. So if you want to hear more about that, check out my poster.
Sherman. I'm a grad student here at UT working with Sharda Jogi. I'm working on the Sheila Hedgeck survey, which is a large area multi-wavelength survey in SDSS Stripe 82. This survey covers approximately 24 square degrees, which is enormous, and it's approximately half of a cubic gigaparsec from redshift 2-ish to 4. The really exciting thing about having such a massive area to study is that we can find really rare populations of massive galaxies, and we can find statistically significant populations of these galaxies. And with that, we can do things like extend the galaxy star formation rate main sequence to the higher mass, higher redshift regime. In order to do this, though, we rely on SED fitting in order to get stellar masses and star formation rates. And the SED fitting of these kinds of galaxies is not always so straightforward. And if you'd like to know more, come talk to me at my poster.
Hi, my name is Milano and postdoc in this organization. And my poster shows a new formation path of fast generation star in the universe. And my simulation newly considers the relative motion between baryon and dark matter as a cosmic recombination error, so very early universe. And this this dynamical pressure suppresses the star formation in the early universe and change the formation completely. And if such a motion is very large, so in cosmic storm region, the very massive, so intermediate massive black hole can form in the universe. And if relatively slow storm exists, massive pulsar binary can form. So this is so pulsar. Thank you.
Hi, I'm Caitlin Stringer, and I'm a third-year graduate student working with Jennifer Marshall, Lucas Macri, and statistician James Long at Texas A&M. For my research, I'm looking for really hard-to-find galaxies and substructure like streams that are orbiting the Milky Way. I'm doing that by looking for groups of RL Lyrae stars. But before I can do any of that, I have to find the RL Lyrae, which is kind of challenging with the dark energy survey data. Although it's very deep and it's wide and it's in the southern hemisphere, so it's a great complement to those northern surveys. It wasn't designed to be a time series survey, so I only have a handful of observations per object across 5 different bands. So if you stop by my poster or talk to me at some point, I'd love to show you how we're taking only a handful of observations, like you can see here, over a period of 3 years, and recovering an RL Lyrae period from them. Thank you.
Everyone. I just wanted to use this minute to advertise a program that we have happening here at UT that many of the folks in the audience are involved with in one way or another, and that's the Texas Astronomy Undergraduate Research Experience for Underrepresented Students program. So that's the Taurus program. It's a 9-week summer research experience for highly motivated undergraduates from across the country, in particular from underrepresented backgrounds. In case you didn't know, astronomy and physics has one of the lowest retention rates for students of color, in particular Black, Latinx, and Native Americans. So we really are focusing on retaining an excellent group of this cohort in astronomy long-term by giving them a home in the astronomy community, particularly here at UT, and also as they apply for graduate programs. And we also have one Taurus alumna who is actually a BashFest attendee, Elizabeth Gutierrez. I just saw her step out before this, but she loved UT so much and her summer experience that she transferred here. So watch out over the next few years if you're on a grad admissions committee for these excellent students.
Hi everyone, I'm Andrew Vanderberg and I'm a new postdoc here at UT. Hot Jupiters are, as their name suggests, hot planets in very close orbits of stars that are about the size of Jupiter. We don't have anything like this in our own solar system, and we want to know how these planets may have formed or come to be where we see them now. We have been studying one particular hot Jupiter system called WASP-47 and a sample of other systems, and we have concluded that these systems probably do not form by a high eccentricity in migration, and most likely form in a dynamically quiet manner. So you can check out the details of my poster. Thank you.
Hi, my name is Visitara Carpenter. I'm a graduate student at Texas A&M working with Casey Popovich. And the purpose of our project was to determine whether or not you can constrain metallicity and age for massive quiescent galaxies using G1 and 2 prism data. And if you can, what interesting things can you say about the metallicity and age? So we did this using the CLEAR survey, which is a prism survey of goods north and south. We then take our sample of quiescent galaxies in a redshift range of 1 to 1.8. We bin them in redshift bins. We fit each single galaxy, derive metallicity and age posteriors, and we can combine those into our separate groups to get metal and age posteriors for each one of our redshift groups. Here's an example of 2 of those. And if you're interested in my metallicity and age results, please see me on my poster.
So hopefully that was too fast for all of you, because now it's time for coffee and you should go to the posters and talk to everyone. about what they just quickly told you about. So thank you.